Hi, everyone. It's a great pleasure to be here. So today I'm going to give an overview of the RISE Lab, a new lab we started at Berkeley last year. So over the past decade, we have witnessed two trends which have already impacted many industries, big data and AI. Today, many organizations gather more and more data, and they do so with one goal in mind: get some value out of the data. This means getting insights of the data, and more importantly, making some decisions on the data, like you've seen in some of the talks earlier. That's why you often hear this phrase that data is only as valuable as the decision it enables. And more of these decisions are taken by AI. So everything from movie recommendations, controlling thermostats, medical diagnosis, trading and fraud detection, manufacturing, and of course, self-driving cars and unmanned drones. However, to achieve the full potential of these decision systems, we need to build these systems such that support mission-critical applications like self-driving on the human life and well-being depend on, and that work in an environment which can be adversarial and is continually changing and sometimes unexpectedly, like you've seen in the demo before. However, besides being accurate, these decision systems need to satisfy 5 requirements. First, real time. If you think about self-driving cars or robotic surgery or fraud detections, you need systems that can make the decisions within seconds or even milliseconds. Second, you need systems which actually learn as the environment changes, continually learn. So consider a fraud detection system of a cyber attack detection system. So these systems have to learn new attacks as they occur, and they need to do so in minutes or even seconds. Third, these systems need to be secure to ensure the user privacy, the confidentiality of the organization data, and the integrity of the decisions. Fourth, you need to develop these systems which are robust. They can handle the complex noise, can handle failures of various components of the system, and more importantly, handle unforeseen inputs. So for instance, a self-driving car should figure out when it's confronted with a scenario never seen before, it was never trained for, and in that case, take a safe decision, like for instance, slow down and stop. And finally, this decision system needs to be explainable. It needs to produce explainable decisions, especially when the decisions are non-obvious. So for instance, we want to know why an AI system made a particular diagnosis, rejected a mortgage application, or led to a particular accident. So RISE Lab, it's about building systems which are going to meet these properties. In particular, the goal of the RISE Lab is to develop open source platforms, tools, and algorithms for real-time intelligent decisions on live data, decisions which are secure and explainable. So RISE, it's an acronym for real-time, intelligent, secure, and explainable. To meet these requirements, at Berkeley, we assembled a team of experts across 4 areas: AI, security, systems, and hardware. RISE Lab started earlier last year and includes 15 faculties and over 70 students and postdocs. It follows a 5-year Berkeley Lab model, which was successful for over 30 years and had some great outcomes in the past. Some of the early labs produced, for instance, the risk architecture, for which Ray Patterson got the Turing Award this year. RISE Lab also follows AmLab, maybe some of you may have heard about. And at AmLab, we are fortunate enough to have impact both in industry and academia. For industry, we build systems like Apache Spark, Apache Mesos, and Alusho, which are today used by hundreds or thousands of organizations. In academia, the alumni of the RISE Lab went to win 3 ACM dissertation awards, and they are now faculties at top universities across the world, including MIT, Stanford, and Carnegie Mellon. The main artifact of the RISE Lab is a RISE stack. The RISE stack has 3 layers. The first layer is platform. And here we have a bunch of storage systems, data management services, authorizations, and authentication services. The second is execution. So here we are developing a set of frameworks targeting AI applications and secure data processing. And finally, at the top layer, we are working with colleagues across the campus and from industry to develop various applications, starting with mixed autonomy traffic, platforms for self-driving cars and robotics, as well as smart buildings. In the remaining of the talk, I'm going to overview two systems we are building at RealTime. One is Ray and the other Helen. Ray is a framework for distributed AI applications. In a nutshell, one way you can think about Ray is a distributed Python plus a bunch of libraries for distributed AI. And initially, we are focusing on reinforcement learning applications. With reinforcement learning, an agent interacts repeatedly with the environment to achieve a task, such as a robot moving an object or winning a game. The agent observes the state of the environment and responds, takes some action which may change the state of the environment, like moving a chess piece on the board. In interacting with the environment, the agent also gets some reward, and the reward basically tells the agent how close it is to achieve its goal. If it's moved an object, how close is to the target where the object should be moved. If it plays a game, how close is of winning the game. And the goal of the agent is to compute this policy, which is a mapping between the state of the environment and an action to maximize this reward. So that's what RL is about. Now, it turns out that RL applications have a diverse set of requirements. In particular, many RL applications, they want to perform to simulate the environment whenever possible, especially in the cases where interacting with the real environment is expensive, slow, or raises security or safety concerns. Just think about robotic and self-driving applications. The agent continually interacts with the environment, and when the state of the environment changes, predict and takes a next action. So this is pretty much akin like serving a model. In fact, a policy is like it's a model, a deep neural network. It's implemented typically by a deep neural network. Finally, as it gets rewards from the interacting with the environment, the agent is updating the model, the policy, typically using SGD, stochastic gradient descent. To meet this wide set of requirements, Ray provides a simple yet flexible API. And to illustrate this API, I'm going to take two very simple examples. So here on the left-hand side, you have a Python code of reading two arrays from two files, file 1 and file 2, and adds these two arrays. And on the right-hand side, it's a simple counter implementation using classes. So what Ray allows you as a developer is to execute these classes and these functions in parallel. And to do so, first, you need to add a decorator, ray.remote, to each function and class you want to execute in parallel. And then when you call these functions, or when you instantiate the class, and you call the method on that class, you also need to add the keywords in remote. So these keywords and decorators will tell Ray to execute these functions remotely as tasks, and the classes as actors. So Ray provides both the task and actor abstractions. Ray also provides a future abstraction in that when you call these functions or the methods, they return a future that is a reference to the result, not the result itself. This allows this execution to be non-blocking, and in turn allows Ray to parallelize this execution. So for instance, these two function calls to read to read the arrays from the file 1 and file 2, they can be executed in parallel because the second remote execution it's submitted right after the first one was submitted. Now, in order to get the result, you need to call RayGet on the future of that result, on the pointer to that result. RayGet is obviously a blocking call, which waits for the result to be available. Also, Ray allows you to specify the resources which are required by executing a particular actor, like in this case, the number of GPUs. If you don't specify anything, by default, each actor or task is going to take one CPU. So how well does Ray perform? As I mentioned to you, is like in reinforcement learning applications, they require to implement basically training, large-scale simulations, and serving. So here I'm comparing Ray with Horovod and distributed TensorFlow, which are highly tuned systems. And this is for a cluster with GPUs. On the right-hand side, you have the cluster size of 16, each node having 4 Volta 100 GPUs. On the y-axis, you see the mean images per second. Here we do HGD for ImageNet. And as you can see, Ray is performing quite well, matching the results of these highly tuned systems. With respect to simulation, here we compare with some of the systems which are used out there for reinforcement learning by practitioners and researchers. And typically, the system they use today is MPI, because MPI provides very high communication throughput. So as you can see, it's again the size of the cluster, it's on the x-axis. The number of simulation per second, it's on the y-axis, so higher numbers the better. Ray is performing quite well when compared with these MPI-based systems. The reason it's doing well because MPI provides its a synchronous system which blocks until all the simulation in a particular stage are done. So if you have a simulation which takes much more than others, the entire system slows down. Ray is much more flexible, and if a simulation takes more, the output of that simulation can be consumed without slowing the entire system. And finally, serving. Here we compare with Clipper, which is a serving system we developed at Rice Lab, sorry. And as you can see, for small models, it's actually performing much better than Clipper, and even for large models. Now, this comparison is a little bit unfair because Clipper is a real model serving system which adds a lot of more features. It provides isolation between the models, it provides model management and so forth. So it incurs additional overhead. So Ray is not really a model serving system, but for our use case, for serving policies, it's more than good enough. On top of Ray, we build a set of libraries. In particular, we released 2 libraries, RLlib, a scalable and composable reinforcement learning library, and RayTune, a flexible hyperparameter search library. I'm only going to present some results for RLlib. And here again, I am going to present some algorithms implemented by RLlib, and I am comparing with some specialized systems, distributed specialized systems, which implement the same algorithms. First is evolution strategy, an algorithm developed and published by OpenAI last year. And it uses a Redis-based implementation. This is a specialized implementation. So as on the x-axis is a cluster size. So here we go up to 8,000 CPUs cluster. And the y-axis, it's a mean time to solve the problem. So lower numbers in this case, it's better. So as you can see, the array is providing, it's matching. In some cases, it's even better than the specialized system. And even better when the size of the cluster exceeds 2,000, while Ray still provides scalability benefits, the specialized system is no longer working. This is another example in which we compare the proximity policy optimization algorithms implemented in RLlib with a specialized OpenAI implementation. Here we are using machines who have GPUs. A server has 4 GPUs and 8 cores. So we use a cluster with up to 16 servers. Again, lower numbers here are better. And again, as you can see, the array implementation matches the performance of the specialized implementation. So the point the takeaway here is that Ray can match the performance of this specialized, highly tuned system, despite the fact it's a much more flexible and easy to use system. Ray is the open source. We released it 1 year almost to the date. And here are some statistics from the GitHub. Of note, the number of contributors is increasing quite nicely. Actually, the growth is accelerating. And as of yesterday, we have 70 contributors. Even more happier, we are seeing some of the early use cases, some of them already in production. A large financial company builds recommendation systems on time-evolving graphs using Ray. Another high-tech company extracts the knowledge graphs from web crawling data. And a very large communication company is using Ray to tune the direction of the base station antenna for cellular networks so that to maximize the coverage or the density of the users changes dynamically, for instance, in the case of an event like this one, or a game of soccer or a show. Also on the research front, OpenAI is currently using Ray to develop the AlphaZero to implement AlphaZero, develop multi-agent RL and derivative-free optimization applications. And also, at Berkeley, multiple teams are using Ray for various applications such as robotics, multi-agent RL, and so forth. In the remaining few minutes I'm going to talk about the second system, Helen, and the goal of the system is to perform shared learning on confidential data, and this is very related with the problems mentioned by Ben in his talk. So here is a setup. You have N organizations which have sensitive data they cannot share. However, they want to compute a global model which will be better than any model they can compute locally. Here are 2 examples to illustrate and to make the case for shared learning on confidential data. And these examples are provided to us by several partners in the RISE Lab. A bank, for instance, wants to cooperate with other banks to improve their fraud detection capabilities. However, they cannot share their data as they are also competing in the marketplace, providing services to the same users. In another example, a healthcare provider wants to have its hospital cooperate to detect flu outbreaks early. If they do so, then they can send vans to vaccinate people, which can save lives and can save also lots of money. However, despite of the fact that all incentives are aligned, these hospitals cannot share freely the data due to regulatory constraints. So the question is, how can this organization compute models without seeing the data? So our answer is Helen, a system we are working. So this is working on. This is preliminary. It's a very preliminary work, and it's working as follows. First of all, when you learn any model, you have an iterative process. In each iteration, every organization computes its own encrypted data and then exchanges encrypted results using multi-party computing to average, for instance, the gradient. Once the iterative process finishes, you have your global model. This Helen provides very strong security guarantees. In particular, it guarantees that even if all the other organizations are compromised, the privacy of your data is guaranteed. So in summary, during this talk, I presented a short overview of the RISE Lab. The goal of the RISE Lab is to develop open source platforms, tools, and algorithms for intelligent, real-time decisions on live data, decisions that are secure and explainable. And also I overview two systems, Ray, a system for distributed AI. It's open source, and you can just use pip to install it. So please go ahead and give it a try. And also I talk about some very recent work, Helen, which allows multiple organizations to learn global models while preserving the confidentiality of their data. Thank you.